Pick up something near you, a phone, a glass, your own hand. Hold it. Feel the weight of it, the solidity, the resistance when you press on it. It is there. It is real. It pushes back. Now let me tell you something about that object that is either going to make you laugh or keep you awake tonight. It is almost entirely nothing. I am not speaking metaphorically. I am not stretching a point for dramatic effect. If you took every atom in that object, every single atom, and you removed all the empty space from inside each one, compressing everything down to just the actual matter, the protons, the neutrons, the electrons, the stuff that physically exists, the object would shrink. Not a little, not by half. It would shrink to a size you could not see with the naked eye. If you did the same thing to every human being on Earth, all 8 billion of us, compressed us all down to just our actual matter, with no empty space, we would fit inside a sugar cube, with room to spare. The atom is 99.999% empty space. That is not a rounding error. That is the structure of matter. And this creates a problem, a very specific, very embarrassing problem. Because if matter is almost entirely empty space, then when you press your hand against a table, you are pressing a cloud of emptiness against another cloud of emptiness. Two nearly nothing objects meeting each other. By every right, your hand should pass straight through. But it does not. You know it does not. You have been pressing your hand against tables your entire life, and it has never passed through even once. So what is stopping it? The textbook answer, the answer you got in school, is that atoms repel each other, that the electrons on the outside of one atom push against the electrons on the outside of another atom, like charges repel. Simple. That answer is not wrong, but it is radically incomplete, and the incompleteness is hiding something so strange, so fundamental, that when Feynman explained what was really going on, he said it was one of the most important and least understood facts in all of physics. Because electromagnetic repulsion does not explain why matter has volume at all. It does not explain why your hand is solid and not a point. It does not explain why the chair you are sitting on has not collapsed into itself. And it does not explain what would happen to the entire universe if one rule, one quantum mechanical rule written down by a 25-year-old Austrian physicist in 1925, was suddenly switched off. Pull on this thread, and the entire structure of matter comes apart in your hands. Let me show you exactly where the standard story breaks down. The electromagnetic repulsion story goes like this. When you push two atoms together, the electron clouds surrounding them get close to each other. Electrons are negatively charged. Like charges repel. So the electrons push back, the atoms cannot overlap. Solid matter. That sounds fine, but ask yourself a more basic question. Why is the electron cloud there in the first place? Why do atoms have volume at all? Why do the electrons sit at a distance from the nucleus rather than spiraling in and collapsing on top of it? In 1911, a physicist named Ernest Rutherford did an experiment that completely changed how we understood the atom. He fired helium nuclei at a thin sheet of gold foil and expected most of them to pass straight through with minor deflections. Some of them bounced almost straight back. It was, as he put it, as if you fired an artillery shell at tissue paper, and it bounced back and hit you. What this told him was that almost all the mass of an atom is concentrated in an unimaginably tiny nucleus at the center. The rest is empty. The atom is almost entirely empty space with a tiny, dense, positively charged nucleus at the core, and electrons somewhere in the surrounding space. And here is the problem that nobody could solve for years after Rutherford's discovery. An electron orbiting a nucleus is an accelerating charged particle. Classical physics is absolutely clear on what happens to an accelerating charged particle. It radiates energy continuously. It gives off electromagnetic radiation, loses energy, and spirals inward. The calculation is straightforward. An electron in a hydrogen atom should spiral into the nucleus in approximately 16 picoseconds. Not years, not days, picoseconds. All matter should collapse. Every atom in the universe should implode in a fraction of a nanosecond. The universe as we know it, you, this room, the planet, everything, should not last long enough to be described. Classical physics predicted the instant destruction of matter, and matter stubbornly refused to comply. Niels Bohr patched this in 1913 by simply declaring that electrons can only occupy certain allowed orbits and do not radiate when they are in them. It worked numerically for hydrogen, but it was, as Feynman later put it, a magic rule with no justification. It said that electrons behave this way without explaining why they behave this way. The real explanation came later, and it is stranger than the problem it solved. In the early 1920s, physics went through a revolution. Not a refinement, a complete reconceptualization of what matter is and how it behaves. The central discovery was this: electrons are not little balls. They are not tiny planets orbiting a nucleus sun. They are not particles in the classical sense at all. They are quantum mechanical objects that obey a completely different set of rules from anything in the macroscopic world. And those rules do not just describe electrons differently, they make electrons fundamentally different. Here is the first thing you need to understand. An electron does not have a definite position. That sentence sounds like it is saying we do not know where the electron is. It is not saying that. It is saying the electron does not have a location to be unknown. Position, in the classical sense, simply does not apply. What the electron has instead is a wave function, a mathematical object that tells you the probability of finding the electron at any given location if you choose to look. Before you look, the electron is not somewhere specific. It is spread out, distributed, existing as a kind of probability cloud throughout a region of space. This is the quantum mechanical picture of the atom, not a nucleus with orbiting planets. A nucleus surrounded by a probability cloud, a smear of electron probability distributed through space in patterns dictated by the Schrödinger equation. The shapes of those probability clouds are called orbitals, and they are real. You can image them now. We have photographs of them. They look nothing like orbits. They look like blobs and dumbbells and three-dimensional flower petals of probability. And crucially, these probability clouds have a specific stable size. The electron does not spiral in, not because there is a rule saying it cannot, but because the wave function mathematics simply produces stable solutions at certain energies. The ground state of hydrogen has a wave function with a most probable radius of about 53 picometers. The Bohr radius. The electron is not orbiting at that distance. The electron is most likely to be found at that distance, but it is genuinely spread throughout a region of space. This is already strange enough, but we have not gotten to the part that explains why you cannot fall through the floor. In 1922, two German physicists named Otto Stern and Walther Gerlach did an experiment that nobody fully understood at the time. They fired silver atoms through a non-uniform magnetic field and measured where they landed on a detector screen. Classical physics predicted a continuous smear. They got two distinct spots. Two, and only two. Nothing in between. Something about the silver atoms, specifically something about their electrons, came in only two varieties. Not a spectrum, not a continuum. Two. This property was eventually named spin. It is not a very good name because it implies the electron is literally rotating, which it is not. The electron is a point particle. It cannot rotate in the classical sense, but it behaves as if it has an intrinsic angular momentum, an intrinsic magnetic moment. And for an electron, this quantity comes in exactly two values. We call them spin up and spin down. Why two? Why not 3 or 5 or a continuous range? This is one of those questions where the honest answer is that quantum mechanics produces this result mathematically. An experiment confirms it, and we do not have a deeper explanation for why the universe is this way. Feynman was asked this question many times, and his answer was always a version of the same thing. That is what electrons do. The mathematics describes it exactly. A request for a more intuitive explanation is a request for an analogy, and no analogy exists that fully captures it without lying. So, electrons have spin. Spin is a two-valued quantum number. Every electron is either spin up or spin down. Keep that in mind. Because in 1925, Wolfgang Pauli wrote down a rule involving spin that turns out to be holding the universe together. Wolfgang Pauli was 25 years old when he published his exclusion principle. He was trying to explain a specific spectroscopic observation, why certain spectral lines in atoms appeared as doublets, as pairs, when classical theory predicted single lines. He needed a fourth quantum number to account for the pattern. He did not know yet what physical property this fourth number corresponded to. That came later when spin was understood. But the principle he stated was this: the Pauli exclusion principle. No two electrons in the same quantum system can occupy the same quantum state simultaneously. In other words, if two electrons share the same location, the same energy level, the same orbital shape, and the same orbital orientation, they must differ in spin. One must be spin up and the other spin down. And since spin only has two values, once you have placed two electrons in a given state, That state is full. No third electron is allowed in. Not later. Not ever. That is the principle. Read it again. Let it sit. Because it does not sound like a statement about why you cannot walk through walls. It sounds like a bookkeeping rule about quantum numbers. But follow the consequences. An atom's electrons fill up available states from the lowest energy upward, 2 electrons per state. Once the lowest energy level is full, the next electrons must go into the next energy level. They have no choice. They are not permitted to go lower. The lower states are occupied. And the exclusion principle forbids any 2 electrons from being in the same state. This is why atoms have structure. This is why the periodic table exists. This is why carbon is not nitrogen, why iron behaves differently from copper. Each element has a specific number of electrons filling specific shells in a specific pattern, because each new electron is forced by the exclusion principle to occupy the lowest available unoccupied state. Remove the exclusion principle, and all the electrons in every atom would cascade down into the ground state. All chemistry vanishes. Every element becomes indistinguishable. The periodic table collapses to a single entry. But we still have not gotten to floors and hands and solid matter. Here is where Feynman pushes deeper. To understand why the exclusion principle prevents matter from collapsing, you need one more piece, the Heisenberg uncertainty principle. The uncertainty principle is often stated as a limitation on measurement. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. But again, this is a statement about a limitation on what we can measure, rather than about the nature of the particle. The reality is stranger than that. The uncertainty principle is not about measurement. It is about what exists. A particle genuinely does not simultaneously possess a precise position and a precise momentum. These are not 2 separate definite values that we happen to be unable to measure at the same time. They are quantum mechanically incompatible properties. The more precisely one is defined, the less precisely the other can be defined. Not because we disturb the particle by measuring it, but because the mathematics of wave functions does not permit both to be sharp simultaneously. Now, suppose you try to confine an electron to a very small region of space. You squeeze its position uncertainty down. By the uncertainty principle, its momentum uncertainty must go up. More uncertain momentum means a wider range of possible momenta, which means on average the electron has a higher kinetic energy. Confine the electron more tightly, energy goes up more. This is not a metaphor. This is a calculation you can do with undergraduate quantum mechanics. The energy an electron must have, simply by virtue of being confined to a region of space, is called the zero-point energy, and it increases as the confinement gets tighter. Think about what this means for an atom. If the electron is too close to the nucleus, it is too confined. Its kinetic energy becomes enormous. It effectively pushes back against the confinement. The electron is not orbiting the nucleus and held in place by centripetal force. The electron occupies a probability cloud whose size represents the minimum total energy, the balance point between being pulled toward the nucleus by electromagnetic attraction and being pushed outward by the energy cost of confinement. The atom has a minimum size, not because there is a rule saying it cannot be smaller, because quantum mechanics makes it energetically costly to be smaller, and the system settles at the size where the total energy is minimized. Remove quantum mechanics, and atoms collapse. Remove quantum mechanics, and matter collapses. But this still is not the full story of why you cannot fall through the floor. Because now we need to combine the exclusion principle with the cost of confinement. Your hand is pressing against a table. The electron clouds of the atoms in your hand are getting close to the electron clouds of the atoms in a table. What happens? The first thing that happens is electromagnetic repulsion. The negatively charged electrons in your hand repel the negatively charged electrons in the table. This is the standard answer. It contributes, but it is not the main event. The main event is this. As the atoms get closer, the electron clouds begin to overlap. The electrons in your hand begin to occupy the same region of space as the electrons in the table. And the Pauli exclusion principle now becomes directly relevant, because if 2 electrons from different atoms are to share the same region of space, they must be in different quantum states. But as the atoms compress together, the available quantum states in that shared region are increasingly full. Electrons from your hand and electrons from the table are competing for the same states. The exclusion principle does not permit 2 electrons to share the same state. So as the compression increases and states fill up, New electrons must occupy higher and higher energy states. The energy of the system rises steeply, not because of electromagnetic repulsion, but because the electrons are being forced into energetically expensive states purely by the accounting constraint of the exclusion principle. This is called degeneracy pressure, and it is one of the most important concepts in all of astrophysics. The force you feel when you press your hand against the table is overwhelmingly degeneracy pressure. It is the Pauli exclusion principle, operating at the quantum level, generating a macroscopic mechanical force that prevents matter from interpenetrating. The floor under your chair is not solid because atoms are solid. Atoms are 99.999% empty space. The floor under your chair is solid because the exclusion principle forbids its electrons from sharing states with the electrons in your chair. You are not sitting on matter. You are sitting on a rule about quantum numbers. Now let me show you what happens when degeneracy pressure is pushed to its limits. Because the universe does this for us in the most extreme environments that exist. When a star exhausts its nuclear fuel, gravity takes over. The star collapses under its own weight. For stars of moderate mass, up to about 1.4 solar masses, the collapse is halted by electron degeneracy pressure. The electrons in the compressed stellar material are squeezed into a state where they are packed so tightly that the exclusion principle generates enough pressure to hold the star against gravitational collapse. The result is a white dwarf, a star roughly the mass of the Sun compressed to roughly the size of the Earth. A teaspoon of white dwarf material would weigh about 15 tons. The white dwarf is solid in the most fundamental sense, not because of chemical bonds or molecular structure, but because the exclusion principle has reached its maximum resistance. But push harder, add more mass. Once the mass of the white dwarf exceeds about 1.4 solar masses, a number known as the Chandrasekhar limit calculated from first principles using quantum mechanics and special relativity, electron degeneracy pressure is no longer enough. Gravity wins. Electrons are forced into the same states as protons, converting them into neutrons by reverse beta decay. The star collapses further. Now it is neutron degeneracy pressure that holds the star, a neutron star. The mass of two suns compressed to a sphere about 20 kilometers across. A teaspoon of neutron star material would weigh roughly 4 billion tons. The neutrons are packed together at nuclear density. The exclusion principle, now applied to neutrons rather than electrons, is the only thing preventing total gravitational collapse. Push harder still. If the neutron star mass exceeds about 3 solar masses, neutron degeneracy pressure also fails. Nothing is left to hold the collapse. The star falls through its own event horizon and becomes a black hole. The sequence from white dwarf to neutron star to black hole is the sequence of the Pauli exclusion principle being pushed to its limits and eventually overwhelmed. The most dramatic events in the known universe are determined by the behavior of a quantum number that Wolfgang Pauli wrote down to explain a spectral line anomaly. Let me state this plainly. The solidity of matter, the resistance you feel when you press on any surface, the reason you do not fall through floors, the reason you can hold a glass without your fingers passing through it, is not caused by atoms bumping against each other. Atoms are 99.999% empty space. There is nothing to bump. The solidity of matter is caused by the Pauli exclusion principle, by a quantum mechanical rule that says no two electrons can share the same quantum state. When atoms are compressed together, their electrons compete for available states. As states fill up, the system's energy rises steeply. That rising energy generates a force that resists further compression. That force is what you feel as solidity. Let me say that one more time, because it is important. You are not touching the table. Your electrons are being forbidden by a quantum mechanical counting rule from sharing states with the table's electrons. The resistance you feel is not physical contact. It is quantum bookkeeping. Every time Feynman was asked to explain why he found physics so extraordinary, he would reach for examples like this one. Not the big things, not black holes or the Big Bang, the ordinary things. The floor, the table, your own hand. Physics performed perfectly, ceaselessly, without anyone understanding it, in every material object in the world. He wrote in one of his lectures, "I want to emphasize that this emptiness of matter, and at the same time this impenetrability of matter, is one of the most striking and peculiar features of nature. We are all used to it. We do not find it strange, but if you think about it, it is very strange indeed. The strangeness is not that matter is mostly empty. We can accept that. The strangeness is that mostly empty matter feels solid, that the vacuum of an atom generates the hardness of steel, that a quantum rule about state occupancy is indistinguishable at human scales from genuine impenetrability. Your intuition says solidity comes from stuff being there. The physics says solidity comes from stuff being forbidden from being there. You have been confused about the nature of solid matter your entire life, not because you were not paying attention, but because the universe has been running a very convincing deception, and the deception is called the Pauli exclusion principle. Once you understand degeneracy pressure, a set of observations that had no clear connection suddenly become variations on the same theme. Why does the periodic table have the structure it has? Why does carbon form 4 bonds? Why is sodium reactive and neon inert? The answer in every case is electron configuration, how the electrons fill up the available quantum states according to the exclusion principle. The chemical properties of every element, and therefore the entirety of chemistry, and therefore the entirety of biology, and therefore you, are downstream consequences of the Pauli exclusion principle. Why does metal conduct electricity? Because the outermost electrons in a metal are in states so close in energy that they are essentially free. They can move through the material without violating the exclusion principle, because there are always nearby unoccupied states to move into. Why does rubber insulate? Because the electron states in rubber are fully occupied up to a large energy gap. To move an electron through rubber, you would have to promote it across that gap. There are no free nearby states for it to occupy without a large energy input. The electrical properties of every material on Earth are determined by how its electron states are filled, which is to say, by the exclusion principle. Why do lasers work? A laser requires a population inversion, more electrons in a higher energy state than a lower one. This is unnatural. Left alone, electrons settle into the lowest available states. Building a population inversion means pumping energy into the system to push electrons upward against their natural tendency to fall. The laser then extracts that stored energy as coherent light when the electrons fall back down. Every laser, from the one in your Blu-ray player to the surgical instruments in an operating theater, is exploiting the exclusion principle's organization of electron states. And there is one more implication worth dwelling on, the one Feynman found most beautiful. The exclusion principle only applies to a specific class of particles, particles with half-integer spin, 1/2, 3/2, 5/2, and so on. These are called fermions. Electrons are fermions. Protons are fermions. Neutrons are fermions. Neutrons are fermions. Neutrons are fermions. They obey the exclusion principle. No two in the same state. There's another class of particles, particles with integer spin, 0, 1, 2. These are called bosons. Photons are bosons. The Higgs particle is a boson. Bosons do not obey the exclusion principle. In fact, they do the opposite. They actively prefer to be in the same state. The more bosons you put in a state, the more likely additional bosons are to join them. This is why lasers work. Photons are bosons, and they can all pile into the same quantum state, producing coherent light. The universe runs on two completely different kinds of particles. Fermions, which are exclusive, no sharing, every particle in its own state. And bosons, which are gregarious, they crowd together, they prefer company, they amplify each other. Fermions build structure, they are the bricks of matter. Bosons carry forces. They are the mortar that holds the bricks together. Remove the fermion's exclusion rule, and matter dissolves. Remove the boson's preference for grouping, and forces vanish. The universe as we know it requires both halves of this divide. I want you to sit with what the physics is actually telling you about your experience of the world. Right now, the chair you are sitting on is pressing against you. That pressure feels like something. It has texture. It has weight. It is part of what makes the physical world feel real, tangible, present. That feeling is the Pauli exclusion principle. Not metaphorically. Not as a chain of causes several steps removed. The direct immediate cause of the pressure you feel when you sit on a chair is a quantum mechanical rule about the permissible states of identical fermions. Everything else, the atoms, the molecular bonds, the cellular structure of the material, those are the scaffolding. But the force itself, the actual thing you feel, is degeneracy pressure, is the exclusion principle, is quantum mechanics operating directly on your experience. You have been feeling quantum mechanics your whole life. Every time you touched anything, every handshake, every step on solid ground, every time you gripped a pen or held a door handle, all of it. Quantum mechanics, Feynman was not the kind of physicist who found this comforting. He was the kind who found it disorienting in the most productive possible way. He wanted you to feel the strangeness of the ordinary, to pick up a rock and understand that what you are holding is 99.999% empty space that feels solid because of a counting rule from quantum mechanics, and to find that more interesting, not less, than the naive picture of solid stuff pressing against solid stuff. He wrote, "It is a great adventure to contemplate the universe beyond man, to think of what it means without man, as it was for the great part of its history, and as it shall be for the rest of eternity without us. From time to time, in the history of the world, a human being of small stature stands up and throws a great light." Pauli was 25. He wrote a rule about quantum numbers, and that rule turned out to be the reason stars do not collapse, the reason the periodic table has structure, the reason chemistry exists, the reason you are made of matter that holds together rather than matter that falls to itself. A 25-year-old writing an accounting rule for electrons, and the accounting rule holds up the universe. I find that wonderful, not despite the strangeness of it. Because of it, commonness is not simplicity. The chair is not simple. The floor is not simple. The hand pressing against the table is not simple. They are all quantum mechanical miracles happening at room temperature, at human scale, without ceremony, billions of times per second in every material object in the observable universe. We just stop noticing, because they happen so reliably. Here is where I want to leave you, and it is a genuine question, not a rhetorical flourish. We say that matter is solid. We say a table is solid, a floor is solid, a wall is solid. But what does solid actually mean in a universe where 99.999% of matter is empty space and the resistance we call solidity is a quantum mechanical prohibition on state sharing? Is the table solid, or is solid simply the word we use for the experience of degeneracy pressure? Is there a difference? And here is the version of that question I find most unsettling. If the solidity of matter is not a property of the matter itself, but of the quantum rule governing the electrons inside it, what happens if you imagine a universe where that rule does not exist? A universe of bosonic matter, if such a thing is coherent. Matter without the exclusion principle. You already know the answer from the physics. It collapses. Everything falls into everything else. No atoms with defined size, no chemistry, no structure, no biology, no you. The Pauli exclusion principle is not a law that matter obeys. It is a law that makes matter possible. Without it, there is no matter to obey anything. That is the thought I want you to sit with. The next time you press your hand against a table and feel it push back, remember what is actually happening at the quantum level. Remember that the resistance you feel is a rule about counting, a rule that says no two electrons can occupy the same state. And ask yourself whether the table is really there, or whether it is simply very insistently forbidden from not being there. I would genuinely like to know where you land on that question.